So we're on part two of the Chapter 17 screencast. This is additional aspects of equilibrium. Today we're going to talk about acid-base titrations, both strong acid, strong base titrations, and strong acid, weak base titrations, weak base, strong acid, weak acid, strong base titrations. So the key with acid-base titrations, if it's a strong acid and strong base titration, it's super easy because you just have to do a stoichiometry calculation, and the leftover acid or the leftover base is how you calculate the pH or the pOH, and then calculate the pH from the pOH. So if you had HCl titrated with NaOH, right? So in this case, you're starting out with HCl, so you have a very low pH, right? And then you're adding OH ions to it, and that's reacting with hydrogen ions, right? Making water, making it neutral, and then all of a sudden it spikes up greatly and then continues to increase after that to the, depending upon the concentration of the hydroxide ion you're adding to it. The reason why the pH starts out so acidic is because you have a strong acid, right? You have nothing in there other than strong acid. And even when you take away some of the strong acid because you're adding hydroxide to it, all the remaining concentration of HCl is in the acid form, right? Because it's a strong acid, so it's a strong electrolyte, so it completely ionizes. But then at the equivalence point, when you reach the equivalence point, you immediately shoot up in pH. And that's because when it's neutralized, you have water, right? That's all you have in your solution is water. And so adding an additional drop of hydroxide is going to drastically change the pH, right? So your equation for the reaction for this example is right here. It's your net ionic equation for the reaction, right? You have hydrogen ions in your acid, you have hydroxide ions in your base, you're reacting to them together and you're producing water, right? However many moles of OH you added, right, is going to react with the moles of hydrogen ion that you had, and then you're going to get water, right? And the other ions don't matter, right? The counter ions, the Na ions and the Cl ions, they don't matter because they're neutral, right? Because the Na ions aren't going to grab hydroxides and go back to form sodium hydroxide. That would be silly. It's a strong base. It completely ionizes when you put it in water. Same with chloride. Chloride is not going to grab hydrogen ions from water and become HCl because HCl is a strong acid, and so it completely ionizes and goes the other way. But what about if you have a weak one that you're titrating with a strong one? Well, in that case, you have the general form of your reaction, right? You have HA for your weak acid, right? And then you have OH minus for your strong base. Because, remember, the OH part is the only part that reacts. The other one is just a spectator ion, right? So if this is sodium hydroxide, it reacts exactly the same. If it's potassium hydroxide, reacts exactly the same as if it's rubidium hydroxide, all those things, right? So in this case, you start out with a little bit of a higher pH, right? You start out with a higher pH because it's a weak acid, and weak acids have a higher pH because they're less acidic. And then, as you titrate it along, you have a region where the pH doesn't change a lot, right? And then you have your endpoint of your titration, which the pH at your endpoint is much different than your pH for a strong acid, strong base, right? It's at a more basic pH, right? The reason why is because the whole time that you're titrating your weak acid, right, you're adding hydroxide to your weak acid, you're making water, but the other thing you're making is a weak base, right? Because A minus, the conjugate base of a weak acid is a weak base. And so that is going to steal hydrogen ions from things. It's able to accept hydrogen ions and go back and form the molecular form of the weak acid, right? So you have a difference here when you're titrating a weak acid, it forms conjugate base. If you were titrating a weak base, it would form conjugate acid, okay? And so at the end point, your solution doesn't just contain hydroxide ions, right? It contains conjugate base ions. So the endpoint of your titration is at a higher pH, and then your pH continues to increase. But after the endpoint of the titration, the concentration of hydroxide ion that you've added in excess actually becomes a bigger factor than the weak base that you form, right? Because the concentration of hydroxide ion that you have in excess is really going to be the determining factor for the pH of your resulting solution. And so here we go. What if you have a strong acid being titrated with a weak base? Well, you're starting out with a higher pH, right? Because you're starting out with a base that you're titrating with a strong acid. And so then you are also going to have a more acidic equivalence point, right? And then at the end point, you're going to have the conjugate acid of your weak base. So that's going to make it acidic, right? Okay, so we're stopping here. And we're just talking about these acid-base titrations because this is a very calculation-intensive topic. So I want to go back to the problem set. Okay, so the homework problems. So if you look at number 33, it just asks you questions about the things that I just showed you, right? So you should be able to do that. And then this asks you about acid-base indicators. Hopefully you have color and you can see that, right? But here's the part that I want to really look at, okay, is 39 and then 43. 43, I'm just going to warn you, is a marathon problem, okay? It takes forever. However, it covers all of the essential topics that you need to understand to really master this concept. Now, this concept is kind of getting above the calculations in questions 39 and 43 are kind of getting above the level that you need to know in the AP exam. However, for full comprehension of this, I feel it's important. And so pay attention if you want to for the next couple minutes as I go over this stuff. Okay, so equivalence point is just a stoichiometry calculation, right? And so stoichiometry calculations, we can do this, right? The key to this is to recognize with HNO3 what kind of acid is that? Is that a monoprotic acid, meaning does it have one dissociating hydrogen, or does it have more than one? In this case, it's one, right? Because it's HNO3. And so one nitric acid molecule is going to react with one sodium hydroxide molecule, right? One H plus ion is going to react with one OH minus ion, right? So you're just doing stoichiometry calculation, and you find out that at the end you have 42.4 milliliters of sodium hydroxide that it'll take to titrate this, right, to reach the endpoint. For the second one, you have a weak acid, but it actually doesn't matter, right? Because it's the same kind of thing. It's a stoichiometry calculation, and it's a one-to-one relationship. So acetic acid is written as CH3COOH. The reason why it's written as this is because it's an organic acid, and the COOH part is the part that's acidic. The CH3 part, these hydrogens are connected to the carbon, and so they are not acidic, right? So it's only one acidic hydrogen. So because it only has one acidic hydrogen, then it's a monoprotic acid, and so you can do the stoichiometry the same way as you would do any other one, right? And in part C, we're doing the same thing again. We just have to start from a different point, so you do different kind of a stoichiometry calculation. However, HCl, again, a one-to-one because it is a monoprotic strong acid, okay? So, simple stuff out of the way. Now let's go with some harder stuff, okay? So we're doing an actual titration in 43 with a weak acid and a strong base. Okay, so you have a weak acid, acetic acid, and you have a strong base, sodium hydroxide. Okay, you're titrating a 35 milliliter sample. Okay, so you know that since they are equal molarities, 35 milliliters of base is going to be needed to fully titrate this to the endpoint, right? But what happens along the way? Is this going to be exciting? The answer is yes. Yes, it's going to be very exciting. So when you start out, you have not added any base to this, right? You are doing a simple icebox dissociation, acid dissociation calculation, right? So you're starting out with your acetic acid, okay, you have that dissociates to the hydrogen ion and the acetate ion. I could include water in this, but it wouldn't change the icebox, right? Because water is a liquid and it's not included in the calculations. So I start out with the 0.15 molarity acetic acid, and then I start out with 0 hydrogen ions and 0 acetate ions, right? Because this is before it is dissociated. Then I have, um, then there's a change, right? I don't know how much it changes, so it goes down by X because the acid is going to break up, right? The molecular acid is going to ionize to some extent. So plus X and plus X over here, and then 0.15 minus X, and then X, and then X. And so when I do that calculation, right, I get a quadratic, and I solve my quadratic, and I get X equals 1.63 times 10 to the minus third. By the way, just so you know, I'm not actually solving quadratics. I'm using a quadratic formula calculator on the internet. Um, you can do this on your calculator, right? Because there's no real need to know the quadratic equation. I mean, you can always just look it up. It's right there if you want it, right? But I just Googled it, a quadratic formula calculator, and then that came up. So just do that, okay? And anyway, then my pH is 2.788. That's what I get when I do this calculation, right? This long way. Now, up until now, I have not told you about this shortcut, but there's a shortcut you can make, okay? Because weak electrolytes often do not want to ionize much, right? Like the concentration of acetic acid is 0.15, but solving our quadratic, 1.3 times 10 to the minus third is the molarity of the acid, of the hydrogen ions that dissociate as a result of this. So that's 0.00163, right? That's much, much less than 0.15. So if that is the case and it's only going to dissociate a little bit, you can save yourself a lot of time and a lot of frustration by not doing a quadratic. Okay, and here's what it is. If you don't do a quadratic, then you can assume that x is much, much less than 0.15. So you ignore the difference between 0.15 minus x, that 0.15 minus x part that makes it into a quadratic, you just ignore it. And then it becomes x squared over 0.15. Then you don't need your quadratic. You just solve it, and you get x equals 0.00164. 0.00164, 0.00163, dude, that's pretty close, so it's okay, right? The pH of 2.784 and 2.788, not much different at all. So use the shortcut, okay? So you can use that shortcut all along. And so we're going to, if you continue through this calculation, I use the shortcut then later when it applies. So when you've added 17.5 milliliters of base, well, then you do your calculation to figure out the moles of acid, right? Figure out the calculation of the moles of base, then the acid is consumed by the base and you have leftover weak acid, right? And so when you have leftover weak acid, that leftover weak acid goes into your concentration of acid, but the amount of base that is reacted is converted into conjugate base. Remember that, right? So the HA reacts with the OH minus and turns into A minus, which is the conjugate base, right? So that goes up here, right, in your concentration of base. So the pH is equal to the pKa at the midpoint of the titration. This is an important concept here, that at the midpoint of a titration, the pKa is equal to the pH in your weak acid titration. All right, so then keep going, right? So we started out, the pH of our solution was 2.78, right? Now we're up to 4.74, right? That's halfway through. Then when we get to almost the end point of our titration, the pH is starting to increase again, right? So I'm reaching my time limit here, so I'm going to stop right here. But you guys continue on with these problems and give it your best shot, see what you can do, and we'll talk about it next week. All right? I'll see you guys later. Have a great weekend.